Hello, everyone. Here we have NYU Blockchain Lab. This is a breakdown of infrastructure from a research perspective. With this is Ayesha Kiani. She is a facility professor and many other things, which she'll tell you about, and Suning Yao, who is a recent graduate. So take it away.
Hi, everyone. Thank you for your time today. So we will be going over through some topics that we've looked into at the research lab. Just for a quick background, my name is Ayesha Kiani. I work at MNNC Group, which is a multi-strat hedge fund. And I also teach at NYU. I teach at NYU's School of Engineering. And over the years, I've had the pleasure of working with various students that have gone to develop projects and research, and Suning is one of them. So I'll give the floor to Suning from here on, who is going to cover all the projects and research topics that we've covered at the lab for past 1 year or so.
Yeah. Hi, everyone. I'm Suning Yao. I'm currently a researcher at Aura, and I am a member of NYU Blockchain Lab. And I just graduated last year at NYU Tandon as an undergrad in CS. So for today's topic, we're going to cover all the different types of infra. For the first one, we're going to talk about network as an infrastructure. For example, L1, L2 blockchains, they are also infrastructure for developers because developers build smart contract on top of them. And also we got compute network and also storage network as the infrastructure because they provide compute power and also storage for data and computing. And also we have a different type of infra, which is protocol as infrastructure. For example, DeFi protocols, Uniswap lays out the foundation for all the DeFi trading activities. And also staking, restaking protocols, they are pretty new. It basically helps you to get involved in the network security. And also, like NFT protocols, we have OpenSea's Seaport and also Blur. They have NFT trading protocols for developers to integrate, and also social protocols like Farcaster. And then we got infra for developers. So these are like the pure infrastructure for developers in their development lifecycle. For example, we got indexers and also rollup as a service and also hosting as a service. And then we got RPC provider as the endpoint for developers to interact with the blockchain, and also execution components, for example, virtual machines. So before we dive into the widely adapted projects and infrastructures from a research perspective, we want to show you guys some research exploration we are working on. So for the AIAG of the current crypto space, we are actually missing a crucial crypto-based infrastructure right now. Because the problem is for the AIAG, we need an infrastructure to solve these three issues. So the first issue is right now we have a lot of AI-generated content. Like Web3 platforms like Facebook, we have a lot of AI-generated images on those platforms because the account want to like increase their activity in the timeline. So they will post a lot of AIGC content. And then for the Web3 platforms, we also see a lot of bots. Like for example, a lot of trading bots. So that's why we need a mechanism like proof of humanity to identify those bots and also the AI stuff. And then we got a lot of deepfake content. So for the deepfake content, it causes a lot of problems. Like for example, in the blockchain space, we got issues about KYC and also authentication. And also deepfake also introduce a problem of violation of a person's reputation. And then we have a final problem, which is about media data. Because today's media always lacks authenticity. And also it's the history of the news and also images cannot be traced and verified. So that's why we need a crypto infrastructure to solve these problems for the AI age. So our experiment is called MPEGs. We explore and tackle the problems with our research project of MPEG. We build an MVP that enables any media data and its processing logic to be verifiable on blockchain. We build it with a ZK virtual machine, and also inside of it, we have the media processing algorithm, and then we have the verifier on Arbitrum. So the general workflow is in the right graph. So first, user will use our front end to capture an image, and then our front end will attest this image. And also, another approach to import the media data is that you can access the media data from like a web page or other sources by cryptography-backed mechanisms. So after we got this import of media data, we can send this into our MPEGs project. So MPEGs project basically run inside of ZKVM, and then we have all those media processing algorithm as the program of the ZKVM. Then the program will take media data as the input and then generate a ZK proof and also compute over those media data. And then this ZK proof can be sent to Arbitron stylus. We have a verifier contract here, and then it will be verified on blockchain. And also, it can make sure that the data and also the computation over those data is verified and trustless. So once it's verified on Arbitron stylus verifier contract, it can make sure that it is forever verifiable because it is verified as a ZK proof and also is stored on Arbitron stylus blockchain. And we're going to talk about some innovations of our research. So for the first point, we implement the full workflow of the implementation. We build out the front end for image input and capturing. And also for the ZK side, we build out the circuit and prover. And then we have the verifier. And we even have like an explorer for our implementation. So this is like a full workflow. And also we implemented some of the media processing algorithm in the ZKVM. It is very extendable to the full FFmpeg algorithm, which is a famous media processing library. And also for the last part, we implemented a Groth16 verifier on Arbitron stylus. One thing special about Arbitron stylus is that it is Watson-based, so it is not like the typical EVM environment. So we need to handwritten all the ZK verifier in Rust to make the ZK proof actually work inside MPEGs. And then these are some challenges we met when we are building MPEGs. So first, the architecture of MPEGs is natively like more complicated than typical dApp. Because when you think about the typical dApp, you have like the front end and also maybe just the smart contract. And if it is the more complicated dApp, like a trading platform, it may also have the server. But for our MPEGs project, we need to also consider all the ZK components. For example, we need to build out the front end and also the server and database for storing the image data. And also we need a prover for setting up this ZK circuit and generating the proof. And also have a verifier smart contract on the blockchain. And also because we are based on images and also media data, we also need a specialized explorer to show all those image data and also transaction history and all the transformation over those image data. And then we have another challenge in terms of the ZK stack choice. So we have several trays to build MPEGs. For the first one, we can write out our custom circuit in a ZK domain-specific language like Circom or Cairo. But we didn't use this approach because it will take too much time to expand to the full FFmpeg logic. And also the second approach that we eventually take is using the ZKVM. Because for using the ZKVM, we can actually write high-level languages inside of this virtual machine to tell it to compile into ZK circuits. So this makes development much more easier and faster. And also we have some traces like ZK compiler, but it actually has more problems when we want to like integrate the whole pipeline. So eventually we take the ZKVM path. And also we have the choice over the verifier. So ZK have a very minimum verification cost, but actually we also need to take consideration of the verifier choice because we need to make sure that our application is scalable, that the verification cost can be minimum, and also if we extend to like a bigger platform, we maybe have like problems with the support and everything. So eventually we choose Arbitrum Stylus because it's more, it's actually more cheaper than the EVM, and also the Arbitrum blockchain is much faster, offering the faster finality and all the verifiable transactions. And then for the future directions, for the first one, we want to extend the features of our MPEGs project. We want to support the full FFmpeg logic. So right now, we implemented 3 commands of the image transformation, but we want to expand to like 3,000 options and commands of the full FFmpeg. So it's basically like building a ZK EVM where you have like 100 opcodes, but for building FFmpeg into MPEGs, we need to like extend to like around 3,000 options. It's like 3,000 opcode. So, and then we want to achieve that use video as input. Right now, we only do competition over image because it has like smaller file size and it is a static image. So for handling video as the input, we need to handle larger file, and this will require continuation feature of the ZKVM. Because right now ZKVM only carries like 16 megabytes of memory, so it's extremely small. So we need to like break a video like down into different frames or like different parts, and then processing it with our ZKVM. And then we think about some of the use cases and platform and application of our infrastructure. So 2 of the ideas I think of is we can build a media rollup based on MPEGs. So we can have MPEGs as the core component to processing all the video and also the metadata computation. And then we can have this rollup as a specific purpose rollup. And then we can also have options to explore composable NFT. For example, we can have variation of CryptoPunks, or maybe we can like combine different CryptoPunks into a large CryptoPunk with like a pop art style art. And then after describing our research projects, we're gonna cover like some breakdown of the infrastructure from the research perspective. And these are all like widely adapted approaches. So for first, we can see that from last year, L2 space grows a lot. Like we actually have more L2s because at the first place, I think we only have like around 5 major L2s. But right now, if you look at L2B data, we actually have around 30 or 40 L2s. So the ecosystem is growing by a lot. And also we see more diverse forms in terms of the tag of L2. Like for the proof system, we can see there's ZK and also optimistic fraud proof system. And we also see a lot of like contestable rollup and also based rollup. And also some of the rollup are based on Celestia and also Bitcoin. So they are taking a sovereign rollup category. And also we see a lot of layer 2 on top of layer 2, which is layer 3. And then if you look at the graph on the right, you can see that we have more adoptions in the L2 space in general. For example, the Ethereum L2 TVL actually flipped other L1 TVL. So Ethereum L2 TVL is really big, and the ecosystem is huge right now. And we also see from a developer perspective, building a rollup is much easier. It is easier to bootstrap a rollup because we have tools like rollup frameworks and also rollup as a service, and even we can like one-click deploy the rollup right now. And then for the protocol as infrastructure, I want to talk more about DeFi. So we see a lot of like programmability into the DeFi space. Take one example is Uniswap v4 hooks. So what it essentially do is that every pool can be customized with programmable logic. So if you look at the graph on the right, you can see that if it is v3, it's just swapping the token. But if it is v4, you can have many like innovation and extension to it. Like you can build like better on-chain price oracle, or you can embed the entire token cell logic into the pool of Uniswap v4. And then another trend we see in the protocol as an infrastructure space is that we see a lot of intent-based architecture. So the idea of intent is that it aims for better user experience and better efficiency. So how it implements that is that they move a lot of the computation and also the components to off-chain instead of on-chain, so that they have more flexibility and also computing power to fulfill users' requests. We have seen a lot of examples of them, like Cow protocol and also account abstraction and Uniswap X. And for the infrastructure for developers, another trend we see when we do research is about VM and compilers. So we see a lot of new ZK virtual machines coming out. For general computation, we see a lot of different flavors of ZK EVM with different types of proof system and EVM compatibility. Also, we see a lot of general ZK VM exploring the foundation with RISC-V architecture, WASM, or they even build their like own architecture set. And also for the compiler side, we see a lot of projects working on AI computation side. Like for example, we have zero-knowledge machine learning, which is ZKML. It essentially generates a ZK proof for the ML inference to make ML on-chain. And also we see like another approach called optimistic machine learning, which uses the fraud proof system just like Optimism and Arbitron to secure the ML inference on-chain. And that's all for the talk. Thank you.
We can take a couple of questions if anyone's interested, or yes.
You mentioned you're generating proof based on the video as an input. What exactly are you attesting? What are you proving here?
Yeah, so basically we are proving the transformation over the image. So when we get the image data, it is actually attested by our front end. So that's why we are like capturing the image from the specific software. So it will like sign the image first, and then we take in this image into our ZKVM. Inside the ZKVM, users can perform some computation over the image, like flip the image horizontally, or increase or decrease the brightness of the image. And then we're going to generate the proof of those images and also the transformations. So for having this transformation, we can have a trace of the history of this image being edited. So that's the basic idea.
Yeah, hi, great work. And I'm wondering what, would you like to introduce more about the architecture? For example, which ZKVM are you using and how's the benchmark? Yeah, thank you.
So for the benchmark side, actually for one operation, for example, increase brightness, it takes about 10 to 15 seconds to generate the proof. But it depends on the input size, because if you have like a very large image, you're gonna perform the computation over like more pixels. So it depends on the image size. And also for the ZKVM, right now we are using RISC-0, but it is like we can use any type of ZKVM if we want to switch to succinct SP1 virtual machine, or maybe VDEM VM. Or actually, we can like use Cairo VM if we want to write the circuit inside of Cairo. So it is fully modular.
Great. Thank you.
Thank you.